This is recorded. Cool. Today we'll talk about length and trig methods. So let me pull out the handout real quick that I wrote. All right, cool. So yeah, we're gonna carry on. Actually, no, we're starting something new. All right. So from in the previous lectures, we introduced Shaver's theorem. So just to quickly recap what Shaver's theorem is. Suppose you have a triangle. Shaver's theorem. So you have a triangle ABC.
There's
So the
nothing
triangle.
wrong with your microphone.
Huh?
I can't hear you clearly.
Oh, is this better? All right, cool, nice. Now, suppose you have a triangle ABC and you have trivians AD, B, and CF. So trivians essentially are lines that sort of contained in a triangle. So suppose we have these trivians, then they are concurrent. So AD, B, CF concurrent. If and only if if only with sort of two things or two theorems. So BD over DC times C over EA times CA no times AF over FB. Or let's just name these angles sines. A, B, actually no, let's just use 1, 2, 3, 4, 5. Oops. So 1, 2, 3, 4, 5, 6. So either that or the trig notation would be sine 1 over sine 2 times sine 3 over sine 4, and so on. So that's Shaver's theorem. It's a very fundamental theorem.
George, is that equivalent to 2 over 3 times 4 over 5 times 6 over 1?
Yes. In fact, you can rotate. Yes, you can do 3, 4, 5, 6, 2, 1, whatever order.
I mean, 2 over 3, 4 over 5, 6 over 1.
2 or 3. Yeah, that's also works. You can start anywhere
Okay.
as long as you go in a circle, more or less. Then you'll be fine. So yeah, so it's a very important theorem in in geometry, and we introduced it before, so we won't spend a whole day on it. But today we can talk about another theorem which I believe I have introduced, and which is quite important, the Menelaus theorem. So here, Menelaus theorem. So Shaver's theorem dealt with concurrence, and the Menelaus theorem would deal with collinearity. So again, we have a triangle. Triangle, and suppose we have a line. So right here, this should be fine. All right, that was not fine, but oh no, that's fine. Okay. So suppose we have triangle ABC, and so there's BC, D, E, F. Then we say these. So D lines on the line BC, lies on the line AC, and F lies on the line AB. And we say that D, F are collinear if and only if we have BD over DC times C over EA times AF over FB. So essentially you're going from, what's the harder thing? Oh yeah. So you're essentially going from like BD. So it's like another train sort of thing. So BD, go back to CD and then CE, AE, and AF, FB. It's just on the longer side. You have to go to the longer side first and come back, sort of. And this also holds when you have this sort of configuration. Oops, no, I don't want to do that. So, actually, no, it's not this. So let's say you have these, you have triangle ABC again. So A, B, C, and then again you draw a line through like this, so that you don't intersect. So the line doesn't actually pass through the interior of a triangle. And you have D, E, F, and then this will still hold. BD over D, C over E. Yeah, I think it's the way to remember this sort of is um the line thing I was talking about. Because so you go with the longer side, and you come back, and then you go shorter side, and you go longer side, and then yeah, so on and so forth. That's how I remember, but you can have your own methods. Yeah, these are two very yeah, three actually almost. These things are very fundamental, and the proof of Menelaus theorem is not really worth mentioning, but in essence, it's very similar to Chavez. You can construct similar triangles with the perpendiculars, and you'll work. And I'll leave you excellent exercise. Cool. Next, we're going to talk about another theorem that's not as frequent, but it's still good to know. So still. So you have a triangle ABC. That's not a triangle. Let's try again. You have triangle ABC. You have a point D anywhere else, segment BC. So core AB is to C, B, and then have lines side A, and this called as M and N. And you'll have, if I remember correctly, should it be C squared N plus B squared M is equals to A squared equals to A. Sorry, guys. Oh, okay, also named this D. So A plus D squared plus N. So the theorem itself is actually not uh, that useful. Is mainly the proof that is a bit interesting. So we're gonna talk about the proof. So yeah, I'll give you a few moments to think about it. All right. So the essence is you see these square thing. So I think very naturally you would think of doing something like the cosine rule. So you can express c squared and b squares in terms of the cosine rule. So we probably have c squared plus d squared plus m squared plus. Let's call this angle alpha. 2dm cosine alpha. And then b squared is d squared plus n squared minus 2dn cosine 180 minus alpha. So c squared n. So we can solve just substitute into the formula. So c squared n will be d squared plus m squared minus 2. So actually we'll just simplify. So with d squared n d square m plus m square n minus 2 dmn so alpha, and then b square m, so b square m is d square m plus n square m plus 2 dm. So you see this sort of a symmetry going on, and if we plus them together,
Did you miss an n? Second equation.
there's an n.
No,
Where?
like no. Yeah, there. So
Yeah, it's very specific.
the very last equation.
Oh yeah, okay. I see. Yeah, 2dm n. If you add these together, and you have yeah, not factorize it. Should I factorize it? I'll just put it here first. D square plus d square m plus d square n. So that's a group. M square m plus mn square is group. And then conveniently, these two cosines cancel out. So I have, let's just factorize this. So d square m plus n plus mn n plus n. That would be m plus n times d square plus mn. Oh, we're done. So n and n plus n is clearly a, with a times d square plus mn. Nice. So this is by cosine law.
Will this ever be useful?
Okay. So for the record, I've never used this in any
Okay.
any contest ever.
Okay.
But it's the proof that we care about. The proof when you can consider cosine law, let's say, is a useful method. And and then for the record, I did use this cosine law to solve the problem. So, for the record. All right, cool. So that's informative, I suppose. And the last thing I'm gonna talk about is a lemma which I don't know how to. I don't know. I don't. Yeah, I don't know the Uh, actually, no, I think I do know. It's a perpendicular criteria. Perpendicularity criterion. So if you have it's not really a triangle. So let's say you have a line. If it's segment BC, and you have points A and D. So points A and D. Then we say AD is perpendicular to BC if and only if AB square minus BD square. No, AD square minus BC square. Actually, well, it's the same thing, but notation wise, this is better. BD square minus DC square. So you connect this, you connect this, and this. And I hope the proof is more or less obvious. So we're going to construct a point E. And then if we arrange this, so hold on. Yeah. So we arrange the B. Yeah. Okay. So AB squared minus AC squared would be use Pythagoras, and there would be B squared plus EA squared minus EC squared plus A plus EA squared. So this triangle and this triangle, and use Pythagoras. EA's cancels out, which is obvious. And you have BE squared minus EC squared. And then similarly, B squared minus DC squared would be B squared plus ED squared minus EC squared plus ED squared, which is also equal to this, and we're done. So it doesn't, you can see, it doesn't really matter what D is. So if you have BC, And you have A and D on opposite sides. This is still true.
Can D be on BC?
If D is on BC, so BD minus D can be on DC, because D would just be E. And AB squared minus AC squared is B squared minus AC squared, and that will work perfectly. As long as they are not all collinear, then it's fine. So A, B, C. And for the record, I've used this in a problem before. So alright, so these are the basic ones. So we're now gonna move to trigonometry. So remember
Wait, George, did you
Yeah.
skip one? I think you skipped one.
I skipped Ptolemy, I bet I skipped Ptolemy.
Yeah.
On this one. This is one of the very first theorems I learned when I started geometry. So no, not meant to draw over. So we have a circle. Yeah, we have a circle, and we have a cyclic chord. So we have a cyclic quadrilateral. And we connect the diagonals. Then we'll have AB times DC. So the opposite sides, the products of the opposite sides, and D times BC. You sum these products together, and it will be equal to the products of the diagonals. Which is, to be honest, is pretty interesting. And the proof, yeah, let me think. And the proof is also pretty nice, from what I remember. Just need to recall. Yeah, okay, I'll leave you a moment to think about this.
Do you use cosine?
From what I remember, you construct a similar triangle because because these two angles are equal.
Oh yeah.
But I don't. I'm trying to figure out the details. Yeah, have a good think about this.
Can you use Stewart's?
Stewart's. Okay, it's kind of hard because if you think about Stewart's, you're using squares, and here there's no squares, and you have a lot of squares to do with. It's pretty annoying.
True.
So I'm gonna introduce proof. Yeah, okay, I think I remember now. Yeah, all right. So you make use of the fact that these two angles are equal. And you draw a similar triangle. So dashed. Such that these two angles so let's call this point. Let's call this point E. Oops. Yeah, so let's call this point E, and you have a, if you remember from last time, we have a spiral symmetry. So these are equal. And in here we have, so you can, basically construct a triangle such that triangle ABE is spirally similar to triangle DBC. And then you very nicely get the ratios AB over, so AB over BD. Yes, you get another nice ratios over BD. So AB over BD, AB over BD would be which one's the useful one? B over BC, I think.
Your triangles do not look similar.
Yeah, that's very unfortunate indeed. Actually, no, it's just an actual DC, yeah, because we're prime through A over DC. And you'll also notice triangle ABD is similar to triangle EBC. So ABD and EBC are also similar. And here you'll get ABD and EBC. So I think AD should be at the bottom. ABD, EBC.
What is that? Why are the triangles similar?
So yeah, okay. So these two. Where was my pen? So these two are equal, and then these two angles are also equal. So
Okay.
yeah, so it just doesn't. My diagrams come bad. So oops. Yeah. So here EC over AD will be BD. The other diagonal, it will be BD over BC. And this, let's move this bit to the left. And this one we have AB times DC. Actually, no, I think that's fine. So we'll have, let me just make this book. So we have AB times A is equal to BD plus AE. B times AE. B times AE. And EC times B equals to BD times AD. Oh no, that is. Hold on. Wait, hold on. But AD, no, so ABD is similar to EBC, right? So AD over EC is equal to, oh, hold on. Yeah, that is not right. Yeah. So AD times BC. This is not right. Okay, so once you have these similarities, you can cross multiply. A times BC is EC times BD. And if you sum these two together, you'll have AB times DC plus AD times BC equals to BD times AE plus CC, which is conveniently AC. And then we're done. So this is a nice use
Can't
of.
see the diagram. Can't see the diagram. Sorry. Wait, so ABD is similar to EBC. Okay.
Yeah.
Okay. Yeah. Thanks.
So that's Ptolemy's theorem, and this also Ptolemy's inequality. So if you have a quadrilateral, so like any convex quadrilateral, actually, I should say. So if any complex, complex, I did not meant to draw a square. Thank you. Convex Okay, never mind. People. So if you have a convex quadrilateral, so let's say that's not necessarily cyclic. Then in general you'll have AB times DC. So again we have the autonomy like statement, but this time will be greater or equals to AC times BD. For the record, I've used Autonomy's theorem in contests before, but I've never used this inequality. So that's Autonomy's inequality. And the proof, yeah, you can basically do the exact same thing, like except that you'll get some inequality stuff, which will make stuff a bit more interesting. But the idea is the same. So if you're interested, you can take a look. All right, so these are length sections, and next I'm going to talk about some other useful sets. So firstly, we're gonna move to more trigonometry stuff. So firstly, we're gonna introduce the angle bisector theorem. I mean, we're gonna record because well, it's a very basic thing. It's not like a triangle. So if you recall the most recent round one of the ensemble, yeah, embargoes is like over ages ago. So yeah, if the recent ensemble round one, it would be really useful if you consider the angle bisector thing. So AD is angle bisector. These two are equal. Then you'll have AB over BD equals to AC over DC. And then, yeah, so these two angles are equal with that. Yeah, I think it is equivalent. Yeah, but then we're going to talk about a more general case, which is a bit more, it's a very common result, very useful. So if you have a triangle, you have any triangle, and you have any point D. So we're going to talk about a more general case now. Then we will have I think sine BAD. Sine BAD over sine DAC will be equals to, that will be BAD corresponds to BD. So BD over DC times B over DC, and then it's AB AC, yes. And then clearly when BD equals DAC, you have the angle bisector theorem. So yeah, again, I'll give you a moment to think about this.
What is this called? The
I actually don't know what this is called. This is just a lemma. That's
okay.
pretty useful.
Then how can I mention it?
You
And
can just prove it. Like it's like a one line proof almost. So
it's a waste of time.
no, true. All right. So again, the proof itself is somewhat more instructive than the lemma itself. So we're going to consider sine law. Oh, yes, okay, whatever. Because we're going to consider sine law. So basically, in this sense, like the use of trigonometry is always to convert angles into lengths, and it's a very useful mindset when considering geometry problems. So sine BA. So if you use sine law in triangle ABD, so then you'll have sine angle BAD. So let's again call this alpha. Sine, oops, it's a bit bad. So sine angle BAD over BD is equal to sine alpha over ABAB. And then triangle ADC, that would be sine DAC, sine DAC over DC, D, be sine 180 minus alpha over AC. And then clearly these two are equal, so we can just take them out and we have sine BAD times AB over DC, BD equals to sine DAC times AC over DC. And when you rearrange, you'll get sine BAD over sine DAC equals to BD over DC times AC over B. Cool. Just give a moment to digest that. So again, we're using the fact that BDs are covalent, and so we can do the alpha and 180 minus alpha operation.
George,
Yep.
according to ChatGPT, it's called Van Elbo's theorem.
I've never heard that name before, but sure. you can probably quote it if
According to ChatGPT,
yeah. Well, the proof is like one line, so to be honest.
I think it's wrong.
All right.
It's not called this.
All right. So when have I used this before? In 2020, 24, 24, you can use this lemma, and then you can do some bash. That's how I did that, which is not the intended solution, but anyways. And yeah, speaking of sine law, I missed one thing. So we're gonna do a little exercise to show why sine law is very powerful. So okay, so actually from the proof you can see, sine law is very useful in transforming angles into lengths and lengths into angles. And we're gonna use um a more practical sort of example. So we're gonna call this is the eccentric lemma config. So suppose you have a quadrilateral. So A B A B A B C D. Okay, that did not work. All right, so A B C D, and you have, and then if this is the angle bisector and these two are equal, then we'll have, and also AB does equal to AD, which is a bit important. And then you'll have ABCD cyclic. And again, we can consider a sine. So in triangle ABC, we have sine ABC, sine angle ABC is equals to AC times sine BAC over ABC, and then sine ADC is equals to again AC times sine CAD over CD. So BAC is equal to CAD. So these two things are equal, and BC equals to CD. So it's nice. So we'll have sine angle ABC equals to sine ADC, which means ABC plus ADC is 180, and we're done. And the reason why we cannot have AB equals to AD is because if AB equals to AD, we will have angle ABC equal angle ADC instead. And this should have become a ABC will be a kite. And this should be like
Wait, what? So what are you trying to prove again?
ABCD is cyclic.
Okay.
Yeah. So again, moving to digest it as usual.
What is it called in center exchange?
Because if you draw a circumcircle and then you have I, right? Then BCC and I and BCCI and CD will be the same by incident accident. So this is the incident accident limit config. So the thing is, it's good to remember your config names because so like personal experience it was 2023 score selection test 3. So I didn't know what this theorem is called, so I just proved it. But I forgot this case. So I probably lost like 1 or 2 marks for that particular problem when I try to use this then. Okay, at the end I made score, but it's a cautionary tale.
Okay.
Somewhat.
Wait.
Mhm.
Wait, but if it's a kite, why would it not work?
If it's chi, then it's not cyclic. Because I mean you can just look at it. Like this thing is not cyclic. Oops. Yeah, like if you have a chi, then the opposite angles will be twice of that one of the angles. So if there's this alpha, then you have 2 alpha and it'll be equals to 180. And you need alpha equals to 90, which is not necessarily the case. So
Wait, what? But if they're the same, then what's wrong in this proof?
then they won't be cyclic because we were trying to prove that they're cyclic instead of a kite.
Yeah. Yeah, but I mean, if they're the same, then what would not work in this? Oh, oh wait, never mind. Oh wait, never mind. I see.
Oh,
Well, I see. Yeah, I see. Sorry.
all good, all good.
Thanks.
Okay. Start it away. Okay. Yeah, I think that's it for the trick session. Now we're gonna move on to some very sus stuff. I sort of just pulled this out because I saw on my book. Okay. To be fair, I've never used these in my life, but just so you know, they might. Okay, I've seen applications of them, but I've never used them in my life myself. So we're gonna talk about some very interesting. Actually, no, I did use them, but not in the geometry context, which is even funnier. But okay. So if you have any triangle ABC, then you'll have the following results. So cosine square A plus cosine square B plus cosine square C will be 1 minus 2 cosine A cosine B cosine C. So in order to, I won't spend too much time trying to prove this. But I think the proof is you move one over and you have actually let's just try to prove it with time. So cosine squared A plus cosine squared B minus 2 cosine A cosine B cosine C. That's sine squared C. I think that looks about right. And then you have cosine A plus cosine B squared minus cosine B cosine C plus 1. Okay, never mind. That's not really helpful. Okay, but you can prove this one on one, but you can I suppose you can just consider cosine law and you can get a massive batch. So we won't waste too much time on this one. The other interesting one was 10a plus 10b plus 10c. This is equals to 10a times 10b plus times 10b times 10c. And again, the proof should
Wait,
be yeah.
it's assuming we have a triangle ABC, right?
Yeah, triangle ABC, yeah.
Oh yeah.
Oh, actually, no, I do remember. Okay, yeah, for both of these proofs, you basically just substitute c equals to pi minus a minus b. And you start bashing. Yeah. And you'll find out, and yeah, it's really not that interesting to demonstrate in person. But that is the idea. I think the next one, I think there's a proof that might be pretty interesting. So then we tie in over 2 times 10b over 2. And then you do a cyclic permutation. B over 2, C over 2 times 10, C over 2. This is actually equals to 1. To see why this is true, I think, yeah, this would be a more or less, there's a more instructive moment. So let's draw ABC. And when you see these half angles, a very natural thing to do is to consider incenter. And another very natural thing to do is to consider the particulars because you're dealing with trig, and trigs are very friendly with 90-degree angles. So it's I, connect to AI, as usual, connect BI, connect CI. DEF. So 10A over 2 would be FI. This is called, yeah, it would be R. R over AF. R square over. So we, yeah. So 10 half, so be BAR, right? And there would be R over FI times R over FI times and then we B over 2 would be R over FB. Oh, no, FA, sorry. And then you have again, and then you'll be a cyclic conversion. So FA over FB. B over 2, so that would be B uh BD, right? Yeah, that would be BD and DC, and you have R times EC times R over A. And then take the R out, and you'll have 1 over FA times FB plus 1 over DB times DC plus 1 over EC times C. And to continue, we can just notice that we can do the what is this called? Okay, I forgot the person's name, but you can do the substitution, which is wait, is it am I high or like am I? Oh yeah, I'm not high. Yeah, so no, remember these two are equal, and then these are equal, these are equal. So you can do a substitution, which is FA is what FA will be. So that's again, so this is C A B, that's C A B. So FA would be B plus C minus A over 2. So FA would be FA equals to AE actually. FA equals to AE, and then FB equals to BD, that would be A plus C minus B over 2. And then EC equals to DC equals to C equals DC equals to B plus A minus C over 2. And you can, yeah, the details will be somewhat annoying, but you can substitute these in, and you should get the equals to 1. I'll leave the details.
Wait, what? Wait. Okay.
You can yeah, I'm like 100% sure, more or less. This is the way to go.
Oh my god. Okay.
But yeah, it's just very annoying. And okay, so the last one would be the last one, which is the more useful one. So alpha I equals to 4 sine A over B over 2 times sine B over 2 times sine C over 2. And this is very interesting. It also equals to that. So again, the second part, you can just substitute C equals to power over C equals to pi minus A minus B, and then you start bashing, and then you get whatever interesting result that you may get. But what I'm more interested in, actually, why is this? Okay. All right. So it should be blue. Yes. So, but the one I'm more interested in is the later one. So it'll be R over 2. So we're going to prove the first one. We're going to prove this. So again, have a moment and think about it. All right. Um, so again, when you have these half angle stuff, it's very useful to consider the in-center configurations. So let's draw a circumcircle. And we consider triangle ABC again. Hello. Abilities.
What?
Okay. No. BA. Yes. Okay. So ABC, ABCD, ABC, and we consider the midpoint arc of BCD. And naturally, this is angle bisector, and naturally we have the incident exit lemma. So here I'm looking specifically. I'm looking specifically at BI. Yeah. So I'm specifically looking at the triangle BIC. So in triangle BIC, by sine law, again we're going to use sine law. Sine BCI over BI is equal BI, and we're going to deal with this thing first. So that's actually sine C over 2 BI, and BI is 2, and then actually, yeah, and then by sine law, this is equals to sine BIC. Actually, no, I think this is what we're doing right now. Sine BIC over BC. And yeah, and then sine BIC is also 90 plus A. So to be sine 90 plus angle A over BC. Yeah, and then if we're going to do one more step. So sine 90 plus A, which is just sine A. Yeah, it's just sine A. And then we're going to do, then the step we're going to do is we're going to put BC.
Huh?
Actually, no, wait, hold on. This is when keep this
No,
unchanged.
it's not.
And then we're going to change BZ into
I suppose it's cosine, right? Or do you not?
sine row, sine row.
No, I mean sine 90 degrees plus A is cosine, is it? No, it's not. Is it? No, it's not. It's not.
We're going to come back to that very soon.
It's negative cosine. It's
It's
negative.
cosine over 2, I think.
Hmm?
Hold on. Oh, wait, no, I wrote this wrong. Oh, that's why. No, that's why. This is over 2. It's over 2. That's why I was confused. Over 2. Hold on. So BC equal 2R cosine because sine A, well, sine over BC is just 2R. By cosine law. Oh, it's substituting. So that's cool. And then you notice BI. So notice you have this is yeah, we're just gonna do one more step. So cosine over 2 over 2R sine A.
It's negative. I think.
Negative.
Negative.
Really?
It's no, wait, what?
Yeah, I'm pretty sure this is correct. The sine 90 plus x is just sine x. I mean cosine x.
Sure. Yeah, that's true.
Yeah, yeah. And we're gonna do one more thing is to actually introduce the radius. So I x do have r, and then we'll have bi is sine c over 2, and then bi would just be so r over bi is sine x. So r over bi is sine b over 2. So bi will be r over sine b over 2. R over sine b, yeah. And then when you rearrange, you have sine c over 2, sine b over 2, sine a over 2. So yeah, you multiply this and you multiply the r over to be cosine n2 over a times 2r over r. So you have your left hand side, which is very convenient. And then no, let me just check this right. Then the 2r and r cosine a over 2.
Wait, how did you get the left hand side of the no? It's the sine c over 2 over r over sine b over 2. How did you get that?
So it's just this times this times this.
No, I mean, how did you get the left hand side of that equation?
Ah, this is bi is that by this triangle.
Uh, oh yeah. Thanks.
What, did I mess with something? Or rearrange the two other side. You arrange it to the other side. Hold up, this is a bit sus. Oh wait, where did I mess up? So sine cosine plus you have sine cosine 9 over 2. You have r and then 2. Wait. Oh, this is slightly awkward. Oh wait. Oh wait, this is sine A. Oh wait, then wait, hold on. This is just wrong. Hold on. Oh, okay, then that makes sense. This is sine A. And okay, let's rearrange for r. Then you should have 2r sine A over cosine over 2. Sine c over r. Sine b over r. And let's put the r here as well. So,
Oh, and then you use the double angle. Ah, okay.
yeah, and by double angle formula, you'll have 4, 2. Cosine, no, cosine, sine b over 2 in space. Yeah, we got there. Nice. I think that's it for today. Yeah, on a side note, this exact formula was used during the prime pursuit speed challenge senior division question 25. So it's somewhat applicable, I suppose. Yeah, these are all the like knowledge stuff